Hello everyone, my name is Raymar Soriano and my colleague here, James Daniel Falcasandos. And we're going to discuss about Laplace transform. But first, we're going to discuss the brief history of where Laplace was named from. So, Laplace transform is an integral transform that is named after the great French mathematician Pierre-Simon de Laplace. Laplace came after his Laplace came after his surname. So he was a French scholar and a polymath who's crucial to the development of many branches of mathematics in statistics, physics, astronomy, and also in philosophy. The pure Laplace didn't actually created those formulas that we use. He has a big part of it that he did so much to develop it, and he deserves the credit for doing such feat. So Laplace transform changes one signal into another according to some rules of equation. It is an integral transform of the given derivative function with real variable t to convert into a complex function with variables. It is second only to the Fourier transform in its utility in solving physical problems and is particularly useful in solving linear ordinary differential equations, such as those arising in the analysis of electronic circuits. How is Laplace used in engineering? Laplace transform is widely used in mechanical, electronics, and electrical engineering. It can also be used to solve differential equations. Linear, a linear differential equation is transformed using a Laplace transform into algebraic equations that can be resolved using a formal algebraic methods. What kinds of circuits can we investigate using Laplace methods? Circuits having any types of source, including resistors, inductors, capacitors, transformers, and or operational amplifiers, can be used as long as the function representing the source has a Laplace transform. So here's the Laplace transform table. We can find the Laplace transform in each equations near to, but instead of finding Laplace transform by its definition, we can look for it in the table instead, but it is much better if we find it by definition. So here are the two Laplace transform method. Here, James Daniel will discuss about the bilateral Laplace transform, while I discuss about the unilateral or the one-sided Laplace transform. So a unilateral Laplace transform is a one-sided Laplace transform that is commonly a common variety of Laplace transform that is usually by the Laplace transform. And it integrates from 0 minus to infinity. From the main use of the unilateral Laplace transform is solving linear differential equations with non-zero initial conditions, which are the system that is not initially at rest. So it is useful for these cases because differentiation property includes a term for initial conditions. The 0 minus is included rather than the infinity or the positive in 0, having systems with singularities at the origin, having impulse function at the time 0. So here's a sample problem for the unilateral Laplace transform. Find the ULT of the following signal. So let's have an example of the differential equation dy over dt plus 2y where x is equals to e raised to 5t times u of t. And the system is not initially at rest. It has an initial condition where the output of the system is y times 0 minus is equals to 1. So first taking the ULT of the differential equation dy over dt plus 2y is equals to x will will, will result to this where the x input of the system right raised to 5t times u of t, the derivative of dy over dt is sy, and for the ULT having the integration from 0 minus and going to be equal to 1, which is after we take the ULT will be simplified to this. The second term 2y will becomes 2 times 2 2 2 times transform of 2 times transform of y, and the right side x we will get the transform of e raised 5t times u of t. The exponential function has a transform of 1 1 1s 1 over s plus a, and a here is the negative 5. Next that we solve for the y. So let's put all the y terms on the left side, transporting the initial condition 1 to the right. And combine all these terms together will result 1 over s minus 4 plus s minus 5 over s minus 5. Using the common denominator here, summing these two numbers together, have s minus 5 plus 1 will sum to s minus 4. So on the right side, we have the s minus 4 over s minus 5, and on the left side, we have the s plus 2 times y. And for us to cancel s plus 2, we divide the s plus 2 on the right side, which result to y is equals to s minus 3, the s minus 4, plus s plus 2 times s minus 5. So here is the Laplace transform of dy over dt plus 2y is equals to x, where x of t is equals to e raised to 5t times u of raised to ut.
So bilateral Laplace transform is a two-sided transform because it can represent both the causal and non-causal time functions. And specifying the region of convergence, or ROC, in solving the bilateral Laplace transform is mandatory because the region of convergence is the range of values in which the integral is finite. So here we have a sample problem. Find the bilateral Laplace transform of the following signal and its ROC. So x of t is equals to e raised to negative at ut plus e raised to bt ut. So to find the bilateral Laplace transform of the following signal, x of t is equals to the e raised to negative at u of t plus e raised to bt ut. We need first to Laplace or transform the x of t. So Laplace of x of t is equals to x of s. And the equation for x of s is the integral of x of t, e raised to negative st dt with a limit from negative infinity to positive infinity. Then from this equation we can now plug in the values from the given problem. So the e integral of e raised to negative at from the given problem, then e raised to negative st from the given equation of Laplace from the x of s dt plus the integral of e raised to bt e raised to negative st dt. Now for the limit of integral, since this is a bilateral Laplace transform, so it is a two-sided Laplace transform, and by two-sided we can imagine it like this, like a sinusoid signal. But since from the original equation the limit is from negative infinity to positive infinity, we can divide it or make it into divide it by 2. So from this side we have negative infinity, the limit is from negative infinity to 0. From this side we have 0 to positive infinity. With this we can use this limit in the equation. So from the so the first part is from 0 to positive infinity, 0 to positive infinity. And for the second part, the limit should be negative infinity to 0. We can now then simplify the equation. So integral of e raised to negative s plus a of t dt with the limit of 0 to positive infinity plus the integral of negative infinity to 0 e raised to um, e raised to e raised to negative s minus b times t dt. Then from this we can now proceed to the integral and the derivation of the formula. We can further simplify the formula by using dt. So the integral of e raised to negative s plus a times t over negative s plus a, limit of 0 to positive infinity, plus the integral of e raised to negative s minus b times t over negative s minus b. Oh, s minus b. Then, since in Laplace, s s s is equals to the uh, sigma plus j omega. With this, we can now insert this function into our equation. So I substituted the value of s or s to sigma. So e raised to negative sigma plus a times t. Tapos e raised to uh, negative 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 j times omega times t over negative s plus a, then times times the limit, so 0 pati 0 pati positive infinity, plus plus e raised to negative sigma minus b times t minus j not omega t over negative s minus b times the limit of 0 to negative infinity, e raised to negative tapos negative lambda plus a, pero instead of t I substituted t, or I changed the value of t to positive infinity. So e times the sigma plus a times positive infinity, e raised to negative j times omega times positive infinity. So e raised to 0 is 1. Same goes to the second e raised to 0 is 1. So minus 1 over negative s plus a plus e raised to negative sigma minus b times negative infinity, e raised to negative j omega times negative infinity. Tapos dito negative 1 kasi raised to 0. E raised to 0 is 1 over negative s minus b. Because this is infinity, we can cancel it out or disregard it. So the remaining value we have, or the answer we can get from this is negative 1 over negative s plus a. So simplify ko na din to siya. So ang answer dito is 1 over s s plus a minus 1 over s minus b. S minus b. Tapos cross multiplication pati siya to further simplify. So pwede pati siya ganito. S minus b minus s minus a over s plus a times s minus b. So final answer dito para sa Laplace transform ng equation is x of s is equals to s plus a s times s minus b tapos negative b or negative b minus a. So ito na yung Laplace transform ng ng given equation natin. Para naman mahanap ang region of convergence natin. So galing dito sa equation, maghanap tayo ng conditions. So dito ROC para sa region of convergence. ROC. So based dito sa equation, sigma plus a or sigma plus a is greater than 0. So sigma plus a is greater than 0. Transpose natin to. So magiging sigma is greater than negative a. Tapos dito naman sa kabila, ito sigma minus b is wait lang, less than pala to siya, less than 0. So sigma, transpose lang, sigma is less than, or b is less than the sigma. So may initial condition na tayo. So ito na, conditions. So pwede nang i-graph or i-plot yung region of convergence. So ang graph ng region of convergence natin is ganito na. So graph dito sa x-axis si sigma, tapos dito sa y-axis is yung j times omega. Galing dito sa condition natin, na galing din dito sa equation. So positive a, so dito positive a, tapos negative b, so a, negative b. Ito na region. So dahil sa condition natin na na negative a or sigma is greater than negative a, so ganito siya, magiging ganito yung parang graph o yung region. Pababa siya kasi negative a. Tapos yung second condition naman natin na sigma is less than b. So ganito naman siya. Pababa din. Pero going from right to left naman. Mag-overlap to sila. Ito sila. So itong dito yung nag-overlap. Ito na yung kuha natin. Ito na yung region of convergence natin. So region of convergence siya. Region of convergence. So yan, na-solve na natin ang sample problem natin para sa bilateral Laplace transform. So nahanap natin ang Laplace transform ng given signal. Tapos which is ito. Tapos nakuha din natin ang region of convergence, which is ito ng graph or itong condition na to.